Swayam Prabha. Digital India. Educated India.
Welcome back to the course Geology and Soil Mechanics. So, in the last lecture we discussed about the unconfined compressive strength of soil, and we discussed about the stress path. So, stress path is very fundamental, as we decided, as we talked about, and today we will be talking about one more type of shear strength determination test, that is vane shear test. So, this vane shear test is very versatile in nature. That means it can be used in the laboratory as well as in the field. So, wherever you are not able to collect the soil sample properly, so there actually you generally perform vane shear test to get the shear strength directly from the in situ condition, right. So, vane shear test, this is fairly reliable results for the in situ undrained shear strength Cu, that is phi equal to 0 condition. You will be getting a very soft to medium cohesive soils may be obtained directly from vane shear test. So, basically this test is generally performed for in situ condition. However, it can be used in the laboratory, though we have several different types of sophisticated tests like triaxial, other triaxial, different triaxial test, direct shear test, as well as unconfined compressive strength determination test. So, these are the tests already available in the laboratory. Apart from that, you have vane shear test, and this vane shear test is only applicable, this is the only test which is applicable to the field as well. So, from there basically we will be getting the undrained shear strength, that is Cu, and for very soft. So, this test is generally used for soft to medium cohesive soil. So, wherever you will be getting very soft to medium cohesive soil, if you see the consistency and all, after seeing that you can decide that okay, you can go for vane shear test in the field itself. So, but please try to remember, if you have very cohesion-less soil or say gravelly soil or maybe very stiff soil, in that situation vane shear test will not be that much effective, or vane shear test should not be used. Okay. So, this is the typical view of the vane shear apparatus. So, what we have one rod, that is the torque is applied on this rod, and you have the vanes like this as it is shown. Okay. So, this is something like you have the rod, cylindrical rod, okay, and at the end of the rod you have the vanes. These are known as vanes. Okay. So, these vanes are attached. The height of the vane will be playing a crucial role, that is a small h, and we are applying a torque T, okay, on this torque rod. Okay. So, through this rod we are applying the torque, and then this is inserted in the ground, okay, and then we apply the torque. So, if you try to think about the mechanism, that I am putting the whole say rod along with the vanes, I am putting inside the soil and then I am rotating it. So, of course, this rotation, when I am giving some action through the torque, through the application of torque, basically you will be getting the opposite reaction, that is the resistance from the soil, and that is purely based on the shear resistance, right. So, and shear resistance will be getting developed along the sides of the vanes, because these vanes will be touching the soil, okay, soil surface, as well as you will be getting the resistance at the top as well as the bottom. When you will be rotating it on the soil body or the soil surface, basically you are rotating it. So, you will be getting the shear resistance along the surface, along the periphery, as well as the bottom and the top, because that is that we are inserting and then we are rotating it. Okay. So, whatever torque you are applying, so that torque must be resisted, okay, by the shear resistance developed at the sides of the vanes, okay, all the vanes, and at the top as well as the bottom. So, that means this torque is resisted by the side moment, okay, given by the side shear resistance, and the moment developed at the bottom as well as the top. So, these moments will be same and the side friction or the side shear resistance will be giving you ms. Okay. And the diameter of the vanes. So, this is the say if you consider this is the diameter. So, diameter of the vane say is small d. So, based on that we will be trying to develop the expression by which you can determine the magnitude of Cu, that is undrained cohesion. Okay. If T is the maximum torque applied at the head of the torque rod. So, this is your torque rod as I told you. So, if T is the maximum torque applied at the head of the torque rod to cause failure. So, we are going up to the failure. So, what is happening? So, you are putting inside I mean the apparatus or the instrument, that is the torque rod as well as the vanes, that is going inside the soil. Now, you are applying the torque. So, you are applying with some constant rate. Okay. So, rate will be a crucial parameter. So, rate of application of torque. So, you are applying the torque with some constant rate. Okay. So, initially you will not be getting any movement of the rod, right. Initially you will not be getting any rotation kind of thing in the rod itself. Then slowly when you will be reaching the limiting state, that means the soil resistance is the maximum soil resistance has been mobilized, at that time you will be getting the rotation. So, that is basically giving you the failure, right. So, and that is your maximum torque which you are applying and which is getting resisted by the shear resistance of soil. So, it should be equal to the sum of the resisting moment of the shear force along the side surface, as I told you, that is nothing but ms of the soil cylinder, and the resisting moment of the shear force at each end, that is me. Okay. So, you will be getting the resistance developed at the top of the vanes, at the bottom of the vanes, and as well as the side of the vanes. Okay. So, therefore, T is equal to ms plus me plus me. So, ms is coming from side, me is coming from top, and me is coming from bottom. So, therefore, because you have two ends, right. So, now we are going to find out the expression for ms. So, what is ms? Ms is nothing but the side resistance developed at the vane surface, right, vane sides. So, ms is nothing but pi d, that is pi into d, that is the periphery, into h. Okay. So, that will be giving you some cylindrical surface, okay, because the vanes are rotating in the. So, because you have the height of the vane is small h, okay, and the diameter of the vane is say small d. So, pi d into h will be giving you the surface area, right. So, surface area on which you are getting the development of the side friction or the side resistance, right, from due to the shear strength. Okay. So, pi dh into Cu will be the total force developed at the surface multiplied by d by 2, that is the lever arm, right. So, that will give you the moment which is getting developed at the surface. So, where d is the diameter of the shear vane and small h is the height of the shear vane, as I told you. So, for the calculation of me, so now you need to calculate me. So, ms you have got from equation 5.43. So, you can calculate ms once you know the say geometrical parameters for the vanes. Now, for the calculation of me, investigators have assumed several types of distribution of shear strength mobilization at the ends of soil cylinder, that is triangular, uniform or parabola. Now, what is that? Basically, if you look at this figure, now the investigators say they decide, they came out with the say solution that, or say interpretation, that the shear strength is not getting mobilized continuously, okay, from from the center of the torque rod. So, this is if you consider this is your top surface or bottom surface. So, at the center of the say torque rod or the vanes, whatever shear will be developed, that will not be same throughout the radial direction. Okay. Throughout the radial direction it will not be same, it will not be, it may not be same. Okay. So, there is some uniform distribution also is considered, it may not be same, it may be same. Now, based on that you are getting three different types of distribution. One distribution is saying that you have 0 shear strength mobilization at the center and you are getting maximum mobilization of the shear strength at the periphery. So, that is given by this distribution, that is nothing but triangular mobilization of shear strength. So, at the center you are having 0 and at the periphery you are having the maximum shear strength, that is nothing but Cu. Okay. Cu is the maximum, beyond that you cannot go, am I right? That is nothing but the shear strength of the soil. So, it is varying from 0 to Cu linearly. So, with the triangular distribution. Now, another set of researchers or the investigators, they are saying no, that distribution should be uniform. That means, it is Cu at center as well as Cu at periphery. Okay. So, that means the distribution is something like this, okay, constant distribution Cu, okay, uniform mobilization of shear strength. Okay. Some set of researchers, some set of investigators, they are saying no, it may not be triangular, it may not be uniform, rather it should be parabolic in nature. So, parabolic means, so this kind of say distribution, okay, where you are having 0 at the center and the distribution is parabolic, and at the periphery you are having the maximum shear mobilization, that is Cu. So, either one of these say distribution you should consider, okay, to calculate or to determine the magnitude of ME. Okay. So, we will see that if you consider different distribution, how your ME will be varying. Okay. So, in general, therefore, so T is equal to the total maximum torque is equal to pi into Cu into d2h, I mean d square h by 2 plus beta into d cube by 4. So, now this part is giving you Ms and this part is giving you twice Me. Okay. So, therefore, from this expression, once you express this T, the total torque to maximum torque is in terms of these parameters, then Cu, that is your nothing but the objective function, right. So, you can determine Cu from this expression, that is T by pi into d square h by 2 plus beta into d cube by 4. Now, what is beta? So, beta is half for triangular distribution, beta is 2/3 for uniform distribution and beta is 3 by 5 for parabolic distribution. So, this will be parabolic, okay, please correct it. So, parabolic distribution. So, I mean now you got an idea, right. So, if you consider, if you say that I will be considering triangular distribution. So, your beta in place of beta you put half and you calculate Cu, because T, this thing you are measuring, right, you are giving the torque with the help of some motorized mechanism. So, from that mechanism you can determine or you can measure the torque which is getting applied on the torque rod. So, you can record the magnitude of T. So, D and H, they are the geometrical parameters for your vanes. So, once you know all those things, you can find out Cu from the in situ condition, from the field itself, which is not possible with some other triaxial test or UCS or direct shear test. Those are purely based on your laboratory experiments, right. So, however, you can get the shear strength parameter from the field itself. Sometimes people, what people do, people find out the Cu value from the laboratory as well as they find out the Cu value from the field and then they match it. So, if you get, I mean, quite a significant amount of difference, then of course, there should be any kind of problem, right. So, if you get quite matching say magnitude between these two values, one from in situ as well as from laboratory, then of course, your test or your determination of shear strength is okay in that way, right. So, this is the way people do the validation or do the comparison kind of thing in the field itself. And one more thing, say suppose if you are collecting the soil sample, basically for your laboratory test you need to collect the soil sample from the soil deposit, that is from the field. Now, when you are collecting the soil sample, at that time during the collection, of course, the disturbance will be there. So, that will disturb the soil structure. So, whatever soil is really or actually available at the site, it may not be same when you are doing the laboratory experiment, right. So, because of your collection and because of your storing and all those things, some structural difference or structural change is happening in the soil. So, therefore, that soil whatever you are taking for the test in the laboratory, so that may not be the true representation of the soil which is lying in the field. So, in that situation, this CU, that vane shear test will give you the CU value from the field itself directly, and which will take care of the actual soil structure which is lying in the field. Okay. Now, vane shear tests can be conducted in the laboratory and in the field during the soil exploration. As I told you, so this vane shear test, so this when you are going for the field, the equipment or the instrument is huge one, and when you are coming to the laboratory scale, the instrument is very small, very tiny. So, you can see, I mean, very say it is really looking like a toy. Okay. So, you can I mean, if you get some opportunity to see this instrument, that is field laboratory experiment of vane shear test. So, basically you must say that. Okay. This is very miniature kind of say torque rod and vanes and all those things, which will be having some motor on top, which will give the torque. Okay. Anyway, so according to ASTM 1994, so if you consider h by d, that is height of the vane to diameter ratio is 2, and which you can of course consider. I mean, generally most of the manufacturers they consider this ratio, and if it is so, then Cu, that is given in kilonewton per meter square, that is the undrained cohesion, is equal to T in Newton meter. Okay. So, T is nothing but the torque which you are observing or which you are recording through the instrument, okay, divided by 366 into 10 to the power minus 8 into d cube, and d is expressed in centimeter. So, if you know d, that is if you know the diameter of the vanes, okay, don't think that this is the diameter of the torque rod. Torque rod diameter is nothing to do with the shear strength. So, this is the diameter of the vanes, that means the peripheral diameter of the vanes, whatever is touching to the soil surface. Okay. So, d is expressed in centimeter and torque is expressed in Newton meter. Please try to remember, this is in centimeter, this is in Newton meter. So, and from this expression you can calculate Cu, which will be coming in terms of kilonewton per meter square. So, in the field where considerable variation in the undrained shear strength can be found with depth, vane shear strength is extremely useful. Okay. So, what does it mean? In the field where considerable variation in the undrained shear strength can be found. So, I mean, you have the soil deposit, you do not have any control to govern that soil deposit, right. That soil deposit is lying. Now, if you see, if you perform some laboratory experiment at different depths at different locations, and if you see the undrained shear strength variation at different locations and different depth is significant, that variation is significant, that means it should not vary that much, right. If you consider like that within a small area the variation is too much or the significant, then you must go for this field vane shear test to get it confirmed that okay, whatever you are getting from the laboratory or whatever you are getting from the field, they are comparable. Okay. So, that is that is why this vane shear test is very useful to get the direct magnitude of the shear strength of soil. The undrained shear strength obtained from a vane shear test depends on the rate of application of T, which I told you initially, that you are gradually applying the torque with some constant rate, right. And this is very similar to your friction chapter, whatever you have covered in 10+2 standard physics, right. So, I mean, if you try to push something on top of some surface, right. So, it depends on the rate also, right. I mean, say if you put this thing very fast, then whatever say dynamic friction whatever will be getting developed, that will be different than if you push that thing very slowly. That means, slow mobilization of the shear strength will be happening, and that rate is very crucial. So, you can apply the torque with very faster rate, then basically you will not be getting the proper mobilization of the shear strength along the surface, you may get some erroneous result. So, it should be very gradual, and that rate will govern the magnitude of Cu. Okay. So, as you give the torque very slowly, so basically if you give the torque very slowly in the torque rod, so what will happen, you will be getting the reverse direction shear resistance, that will be getting mobilized. So, slowly the shear resistance will be getting mobilized and gradually, so there should not be any jump, right. So, if you do it fast, so that mobilization will not be happening very fast. So, this mobilization needs some slow or the gradual movement of the torque rod or the vanes. Okay. So, Behram in 1974 also showed that as the plasticity of soil increases, Cu obtained from vane shear tests may give results that are unsafe, and he suggested the correction. Now, what Behram has suggested, Behram in 1974 he suggested that if the plasticity of the soil increases, and you know how the plasticity of soil increases and what is the parameter by which you can determine the plasticity of soil is getting increased, right. So, plasticity index, right, whatever you have seen earlier. So, if the plasticity of soil increases, then whatever Cu value you are getting from the field by vane shear test, that may be little bit unsafe, right. So, that means that will be predicting, overestimating the magnitude of Cu. So, you must apply some correction factor whenever you are getting or whenever you are dealing some high plastic soil. Alright. So, the Cu design, that means that is the design value of Cu, whatever you will be proposing, that is equal to lambda into Cu obtained from the vane shear test. So, this is your, this lambda is nothing but the correction factor, and it is given by this expression 1.7 minus 0.54 log plasticity index Pi. Okay. So, as your plasticity index increases, you will be getting different value of lambda, and based on that you can find out the Cu design. So, what is that is equal to lambda into Cu obtained from the vane shear test. So, this is your actual Cu multiplied by lambda will give you the design value of Cu. Okay. So, this is the correction Behram has proposed. Otherwise, if you do not do this correction, whatever Cu you will be getting, that will be giving you a little bit unsafe, that means it will be overestimating the strength, which is not actually available in the soil. Now, we will be learning two very important terms, one is the sensitivity of soil, another one is the thixotropy of clay. Okay. So, for many naturally deposit clay soils, the unconfined compression strength is greatly reduced when the soils are tested after remolding without any change in the moisture content. Now, what does it mean? So, suppose you have the clay soil in the field, now you are collecting the soil sample, okay, from the field, and then you are doing some unconfined compression strength test in the laboratory. Now, how you will collect the sample? So, you have several options to collect the sample. Okay. You have the sampler, proper sampler, which will be which can be attached to the SPT test, or you can collect some undisturbed sample. So, there are several ways to collect the sample. So, though that is not in the scope of this particular course, that is coming in the soil exploration and investigation. However, so you can collect the sample, okay, and your objective or your intention will be always to collect as much as you can collect the undisturbed sample, right. But it is not always true. I mean, in the field, whenever you will be collecting the sample, it may not be true that all the times you will be collecting the undisturbed sample. So, there will be some amount of disturbance, right, and this disturbance will affect the shear strength of the soil greatly. So, if the soil is very sensitive, then this disturbance will be causing significant amount of variation in the soil, I mean shear strength. If the soil is not that much sensitive, then you will not be getting that much of variation, right. So, it depends on the sensitivity of the soil. That means, whatever soil you are collecting, so that soil is a undisturbed soil in the field, whatever is lying in the in situ condition, that is your undisturbed soil. Now, you are collecting the soil, you are collecting the sample, and then you are you are collecting the sample for doing the laboratory test to find out the shear strength, right. Now, how that shear strength will be getting affected, or how the variation will be you will be getting in the shear strength parameters, whatever you are expecting to get from the field, that is from the undisturbed sample, and whatever you are getting from the disturbed sample, this not disturbed, remolded sample. So, that is known as remolded sample. That means, you are remolding the soil, I mean to perform the shear test. So, if the soil is very sensitive, then basically you should be very much careful, and that will cause the variation, significant variation in the strength, shear strength parameters, right. So, that you must take care, you must take enough care when you are performing the test. So, first, so this property of clay soil is called sensitivity. Okay. So, if I say my soil, clay soil is very sensitive, then you have to take the utmost care, and you should know. Okay. I mean, if I say the sensitivity is say 2, or if I say the sensitivity is 4, then you should know that whatever I am getting from the laboratory experiment, from the unconfined compression strength test, okay, that may not be the same, okay, whatever is actually lying in the field. Okay. So, this sensitivity will define that, will talk about that kind of variation. So, the degree of sensitivity. So, now we are going to quantify this sensitivity. The degree of sensitivity is given by ST is equal to QU undisturbed, that is whatever is actually available in the field or the in situ condition, divided by QU remolded. So, that basically this value you are getting from the laboratory experiment. Okay. So, if you know the sensitivity of the soil, or how you will get QU undisturbed, maybe you can go for Venn shear test, and you can get for this QU value, right. This is the way you do, and QU remolded, that you can go for any triaxial test, or maybe unconfined compression strength test, and you perform this. So, to get this QU remolded value. Okay. So, the ratio of these two will be giving you the sensitivity. Okay. Now, basically if you see the unconfined compression strength for undisturbed and remolded clay with time, with axial strain. Okay. So, this is your sigma 1 say, because in unconfined compression strength only you apply sigma 1. So, as you go on increasing, because you do not have any sigma 3, you do not have any cell pressure. So, as you go on increasing sigma 1, okay, or rather sigma 1 is increasing, your axial strain is also increasing, right. So, in case of remolded sample, you will be getting the curve like this, whereas in case of undisturbed sample, you will be getting the curve like this. Now, this is the maxima or the peak, that is nothing but the QU undisturbed, and this is nothing but QU remolded, okay, this point. So, now you see the difference. Okay. So, this is the difference between these two. Now, if soil is very sensitive, this difference will be greater. If the soil is not that much sensitive, this difference will be coming down or decreasing, right. So, it depends on the sensitivity, how much sensitive the soil is. So, when you are collecting the soil sample from the field. Okay. So, based on this sensitivity, you can say, okay, this, I mean, see, if this QU value, or if you know the sensitivity of that particular value or particular soil, then basically you can calculate QU undisturbed from the remolded value of QU. Okay. Now, ST of most clays ranges from about 1 to 8. So, if it is 1, then this is not at all sensitive, that means QU undisturbed is equal to QU remolded. So, this is not at all sensitive. Now, if the value or the ST value is increasing, that means the soil is becoming more and more sensitive. So, if I say my soil, I mean sensitivity value, degree of sensitivity of a particular soil is say 7, and if a soil is having degree of sensitivity value of say 2. So, that 7 ST value of 7 will be more sensitive, and whenever you are collecting the sample, whenever you are doing some test on the remolded sample, you should be very much careful. The loss of strength of clay soils from remolding is primarily caused by the destruction of the clay particle structure that was developed during the original process of sedimentation. So, this is, I mean, why you are getting this variation, why at all you really need to think about this kind of remolded sample and undisturbed sample, because the during original process of sedimentation soil has acquired some structure, right, as we have discussed, like flocculated structure or whatever structure. So, during the process of sedimentation soil has got some inherent structure. Now, when you are collecting the soil, though you are not changing the moisture content and all, but still you are changing or you are disturbing the structure, whatever structure the originally the soil had. Okay. Now, you are changing the structure, and due to this changing or you are destroying the structure, and due to this destruction basically you will be getting different, I mean lower strength, right. Whatever strength you are supposed to get in the field, you will be getting rather lesser value of strength, okay, shear strength, okay, in the laboratory. So, that means if you design with QU remolded, basically if the soil is not very much sensitive, then if you design any structure based on QU remolded, then it is okay. But if the soil is very sensitive, and if you are still designing with the value of QU remolded, then basically you are underestimating the soil strength. So, whatever design value you are considering in the field, actually it may be more than that. So, that depends on the sensitivity. Okay. If however, after remolding a soil specimen is kept in an undisturbed state, that is without any change in the moisture content, it will continue to gain strength with time. This is very interesting thing in the soil. So, what does it say? If however, after remolding a soil specimen is kept in an undisturbed state, undisturbed state means you are not changing the moisture content. Okay. So, you are collecting the soil sample, which is now it is remolded sample. In the remolded sample you are not changing the moisture content, that means you are taking enough care, so that the moisture is not getting lost from the soil matrix. Okay. Now, you are keeping that thing. So, with time it will continue to gain the strength. So, whatever strength it had in the field. Okay. So, it will try to approach to QU undisturbed. Okay. So, this is very interesting thing. So, with time basically soil will gain the strength. So, this phenomena is referred to as thixotropy. So, this is very important parameter and very interesting characteristics of soil. So, with time it will gain the strength, and that is known as thixotropy in soil mechanics. So, now we will explain this thixotropy behavior or thixotropy cycle for any kind of soil. So, this is for complete thixotropic material. So, what you have? So, this is along the y axis you have strength, along the x axis you have time. So, strength versus time we are plotting. So, at the initial, this is your initial undisturbed strength. So, this is your initial undisturbed strength. Okay. So, QU undisturbed you have. Now, basically you are collecting the sample, that means you are remolding the sample. So, you are losing some strength, and that is say QU remolded. Okay. So, this is the difference between QU undisturbed and QU remolded. This is the difference. Okay. So, now it depends on the sensitivity. As the soil is becoming more sensitive, this difference will be more. So, anyway, so this remold, after remolding you will be getting this much of reduction in the QU value. Now, if you keep that thing as it is without change in any moisture content, as I told you, then it will basically harden, it will gain the strength with time. So, that is along this x axis is the time. Okay. Along with time it will gain the strength, and it will try to reach the same magnitude of QU undisturbed. That means, it will regain its own strength, whatever it was, I mean whatever it lost actually. Okay. So, whatever it lost, so now again it is coming back to the soil. So, this phenomena is known as thixotropy. So, this is known as complete thixotropy. So, after that again if you remold the soil sample, it will come down to this. Again with time it will regain its strength, and it will become the same soil whatever you had in the field. Okay. So, this is very interesting phenomena. I mean very few materials in the world, okay, which will be showing this kind of characteristics. Okay. So, and that is why maybe initially if you disturb the soil, after certain times the soil will regain its strength. So, that happens actually. Okay. Anyway, so this is known as complete thixotropy. That means, whatever the soil is losing, the same amount of strength it is regaining after certain time. Now, sometimes you may get partial thixotropy. That means, you started, so this is along strength versus time, again we are plotting. So, this is your initial undisturbed strength. Okay. Now, you are disturbing the sample, you are remolding the sample, and with remolding you are getting, this is your remolded strength. Okay. Now, with time the soil will regain its strength, but it will not reach to its original undisturbed strength, original or the initial undisturbed strength. Rather, it will be regaining, but it will be lying here. So, that is in between your remolded strength and the undisturbed strength. So, but it will regain, of course, it will regain. So, this is known as partial thixotropy. That means, it is not going back to its original or the initial undisturbed strength, rather it is going to some in between higher strength, right. So, after that again if you remold it, okay, it will come to this point, again it will regain, and that regain will be same, but every time it is regaining the strength at this level, it is not going up to this level. So, that is why it is known as partial thixotropy. So, you will be getting some amount of regaining of strength, but that may not be the exactly same whatever the soil had lost during the first collection of soil sample. Now, for soils, the difference between the undisturbed strength and the strength after thixotropic hardening can be attributed to the destruction of clay particle structure that was developed during the original process of sedimentation. So, what is the reason behind this partial thixotropy? That means, you are not going back to the original position. That means, you are destroying the original structure of the soil. So, this destruction will cause that you will not be getting the same regain, or it is not going back to its original position, because you have destructed or you have destroyed, okay, some amount of soil structure. Okay. So, I will stop here today. So, in the next class we will talk about the Skempton pore pressure parameter, how to find out Skempton pore pressure parameter and how to obtain those parameters. Whatever parameters you have seen, already we have discussed Skempton pore pressure parameter A and B. Now, we are going to find out how to obtain the values of A and B. So, in the next class we will take this. So, thank you very much.